And you might want to put your units down, because you can't type them in. Had 2 brave souls so far. All right, I'll give you 1 more minute.
Do we have to send the Frankie Wood? Do we have to do that every day?
Yeah, you do it once during the first, that first time during the class you do it. You type in that Frankie Wood B389 the first time during class, and then after that, anything else I do in class, you just have to do the 37607.
Okay.
Got a couple of different choices in here. Give you a second to type it in. All right, I'm going to switch to the back of the camera. We're going to calculate it and see who, you saw the different answers, saw what different people put in there. So let's, hopefully the back of the camera comes to life. Maybe. Try it. Now try it. See. Just thinking about it. There we go. Sort of. Maybe. There we go. Now we got it. We got it. So, all right. So remember, if I'm doing spring constant, I'm going to use Hooke's law. So the force due to the spring is going to be minus kx, and I have to keep track of what that minus sign is. The force that I've got going was my mass times gravity, and we used 110 kilograms. Gravity is 9.8 meters per second squared. And that gives me my force that I'm going to have. And if I plug that into the calculator, just for grins and giggles, because you can't do this all as one step. So this is 1078 newtons. So that's the force that was put on the spring. The change that I had was a negative 13 centimeters, or it was a negative 0.13 meters. So that's going to give me my meters. So now if I rearrange the force equation, K is going to equal the force divided by my negative x. My force that I've got going in here is the 110, or the 1078 newtons. The negative x is negative 0.13 meters. And when I plugged it in the calculator and rounded it to 2 significant figures, that's what I got. Divided by 0.13. Yep.
If it doesn't ask for specifically Newton per meter, could you do it Newton per centimeter?
The question over there in Enid was if they don't ask specifically for Newton per meter, could you do it in newtons per centimeter? Yes. But I'm gonna flip back to the computer and I'm gonna show you something. Let's see, computer, present. That means you have to be careful when you type in your units. Because if I look right here, somebody forgot to make the change from my Newton to Newton meters to Newton centimeters.
I was the one who did a unit, so like I was so bad about that.
Yeah. So so especially on an exam, because sometimes Newton centimeters actually makes more sense than writing it in Newton meters. The standard is Newton meters, but sometimes actually what your problem going forward makes a lot more sense being in Newton centimeters. Not having told you what the next question is going to be, you could have, that Newton centimeters would have been fine, just as long as you documented that it was Newton centimeters. So let's do another one. I've got a different one, so I'll go back to my polls. So we're going to use that same spring. Let's see. I thought I was going to do that. Let's create. Maybe I didn't create it. I will create it real quick. So now we're going to ask, what would the acceleration of the rebound of the spring? So we're going to take the box out of the trunk when the box is removed. Oh, I want just good old open-ended, create, and it's out there. So now we've calculated the spring constant, and we want to know what the acceleration of the trunk is going to be when the box is removed. Because we all have seen that, right? We lift the box out of the trunk and then all of a sudden it bounces back up, right? We want to know what that acceleration is. And I just want the magnitude.
Okay, somebody be brave.
Got somebody brave? Good. Woo! Come on, it's easy to be brave because nobody passed it up with their name in there. Because it's taking you so long, I know you guys have made it way harder than it is. All right, give me one more minute and then we'll get going. All right, I'm gonna switch over to the document camera. You guys can kind of see, kind of think through this a little bit. So that was the spring constant, as soon as it gets to the document camera. That was the spring constant that we started with. So I could actually go through the calculation if I wanted to, or I could do something a little different. So this is my force equation for a spring. But my force is also equal to my mass times my acceleration, which is equal to that right there. So if I'm looking at what my acceleration is, I can do this by inspection and show that my acceleration is gravity. So my acceleration, just by inspection, is going to be 9.8 meters per second squared. So when you guys are taking your MCAT or whatever exam that you're taking to get into graduate school, and it gives you your different numbers, you can actually look at it and kind of think through it, and without even using your calculator or out even plugging it into it, you can actually say, oh, that's just going to be good old 9.8 meters per second squared. So so don't necessarily make it harder than it has to be. But if I go ahead and do the calculation, right? So let's go ahead and do the calculation. I've got MA is going to equal to negative KX. I'm only concerned about the magnitude, so I can go ahead and say MA is equal to KX. And my acceleration is going to be my KX divided by M. And so now I've got my K is 8,300 Newton meters. My X was my 0.13 meters, because we're assuming that my spring didn't deform, and we're assuming that it's going to rebound completely, and my mass was 110 kilograms. And when I plug that back in, I get my acceleration as 9.8 meters per second squared. So if I'm working with my units, I want to make sure I'm getting that meters per second squared so that I can actually see where my units are. And if I want to go ahead and do the unit analysis, so there's my Newton per meter times meters divided by kilograms. Meters cancel, so I've got Newton kilograms. My Newton is a kilogram meter per second squared divided by kilograms. Kilograms cancel, and I get my meters per second squared for my unit analysis. So I can show that I did it in the right area. So you're likely to see some sort of spring constant problem on our exam. I mean, you're pretty likely to see that. We've been working with them for a couple of days, so we're going to work there. So now I've got another one for you, because the other thing we've been working with is writing the wave equation. And your simple harmonic motion wave equations for your video are due on Wednesday. Okay? Simple harmonic motion due on Wednesday, and with the wave equation. So now I want you to kind of write a wave equation. I did do a poll for this one, so I'm going to leave that up for a second so you can write it down on your piece of paper. Write the wave equations for this one, and we can go from there. Oh, I meant to bring the pendulum today. I'll have to put a note and do the pendulum on Wednesday. I will write myself a note. I was at a conference this weekend, so I know why I forgot. All right, so hopefully you guys had a chance to write out the wave equation for this one. So the first thing when we're writing out our wave equation, remember our wave equation that we're going to be working with is this right here. Remember in the lab, you're probably going to be using the sine instead of the cosine. So it's 2 pi times the frequency times time plus the phase angle. Now, when it's cosine and I start at 0, I want the cosine of whatever the angle is to equal 0. And if I happen to remember it, I can actually plug it into my calculator. We know that the angle would have to be 90 degrees if I'm in radians, because I'm going to want to be in radians. My phase angle is going to end up being 90 degrees, which is also going to be pi over 2. So that will give me my 0. So this phase angle, when I'm doing cosine, is pi over 2. We did this same problem on Friday, but we used the sine instead of the cosine, and that phase angle was 0. So that's all related to where I'm starting my wave that I've got. It's all related to where that wave starts. So that's the first part of the problem. The second part is we've got to figure out what the amplitude is. So the amplitude of the wave that I drew, and I actually gave it in meters, the amplitude is in 10 meters. So that's the amplitude of this wave. The period of this wave, if this is in seconds, I want the time that it takes for one complete cycle, and I intended to draw it such that one complete cycle was 8 seconds. So the period is 8 seconds. So the frequency is equal to 1 over the period. So that's 1 over 8 seconds, which is going to give me hertz. And when I plug that into the calculator, just so I got it, I get 0.125 hertz. So now I've got the frequency, I have the period, I have the amplitude, and I have the phase angle. So now I can just write the equation. So I'm going to get a piece of paper here, I'm going to slide this down. So now I'm gonna write the equation. Y is gonna equal 10 cosine 2 pi, and I put my 0.125 t plus pi over 2 is my raw wave equation. If I want to clean this up a little bit, I get my 10 cosine, and I would do it like this. I would do that 0.125 times 2, so I would say it's 0.25 pi times time plus pi over 2. Or I could do it 10 cosine pi over 4 times time plus pi over 2. And then you can simplify it down even further. So it just depends on how far you want to simplify it down. But that gives you your wave equation with respect to time for simple harmonic motion. So we will get that lovely wave equation. Just as a kind of reminder, if I wanted to know what the angular frequency was, remember my angular frequency is 2 pi times the frequency. So in this thing, I could read it right off of my wave equation, and that gives me pi over 4. And if I did that, remember that my omega is also equal to the square root of my spring constant divided by the mass. So I can get a whole bunch of different pieces of information right out of that wave equation. So I can play with that and get a lot of that information out there. So just kind of getting you back on track as to where we are. So where we finished on, let's do this, enable editing. Where we finished on Friday, here, was this right here. We talked about dampening. Just thinking about it. Talked about dampening. My dampening in a system can come from some sort of friction. So if it could be air resistance, and I'm slowly going to reduce that amplitude, and that amplitude decreases with time. So I will actually get that dampening. So now let's start talking. The reason we start with simple harmonic motion is it gives us a good way to start coming into talking about waves. Your next assignment that I'm going to release from a video standpoint or a recording standpoint, and I will get it up on Blackboard by Wednesday, is we are going to actually start talking about the Doppler effect. So I want you to start thinking about the Doppler effect. We all know the Doppler effect. That's the change in the frequency that we hear when a train whistle goes by, or when a siren goes by, or something along those lines. What I'm going to have you do is very similar to what we did with the simple harmonic motion. I want you to capture, either by video or by just a sound recording on your phone, something that's demonstrating the Doppler effect. Because I like to hear the different Doppler effects. So I really don't necessarily want to hear a siren, because I've got like 50 sirens, right? I've got a bunch of sirens. I really don't necessarily want to hear a train whistle, because I got a bunch of them. But there are lots of things that you can actually hear the Doppler effect in that aren't a siren and that aren't a train whistle. But those are the two common examples that we have. So I want you to kind of think about it, and then I want you to record one, and I want you to send it to me, email or upload it on Blackboard when I get it posted, and I'll have it posted by Wednesday. And the idea is to have that probably by Monday's class, because Monday we'll get to the Doppler effect. That's kind of about where we'll hit the Doppler effect. So it's a lot of fun to have everybody else's Doppler effects instead of the ones that I pluck out. It's because you get to hear some different things. I will tell you there are some unique ones out there. There are some fun ones out there. But let's talk about waves. We all are familiar with waves. And if you drive by any pond this morning, you'll see lots of wave action in the pond. The wind is driving a lot of waves. So we've got a lot of that kind of pieces out there. So simple harmonic motion gives us a way to express how we're going to do a wave. We are going to be talking about mechanical waves right now. In chemistry, you guys have already heard and looked at electromagnetic waves. That's light, electrons travel by electromagnetic waves, and we'll get there. But sound is a mechanical wave. That wave in the pond is a mechanical wave. And so we're going to start with those mechanical waves. So we're going to define a wave as some sort of, it's a motion of a disturbance. We look at that surface. If I have a placid pond and I drop a pebble in it, we generate a wave, and we see that motion disturb the surface of the water. We actually get that disturbance. Some of you may have felt your bread vibrate this morning. It was right around 4:45-ish, if I read the clock right. It's either 4:45-ish or 5:45, because right now I don't remember if it were a 6-hour subtraction from universal time or a 5-hour subtraction because of daylight savings time. But it woke me up. I felt the bed vibrate, and we had an earthquake out of Hennessy this morning, a 3.5 earthquake out of Hennessy. And so most of you probably could have felt it. You may have slept through it, but you could have felt it. It's a mechanical wave. We had a disturbance of the surface of the earth, is what we had with that earthquake. There are 2 types of waves, and we'll talk about those, and earthquakes generally have both types of waves, so we'll definitely talk about that. But a wave is the motion of a disturbance. Mechanical waves, when we talk about mechanical waves, those are different than electromagnetic waves, but a mechanical wave has to have some source of the disturbance. Something that energy release for the earthquake, the pebble that drops in the water, my vocal cords creating a vibration for sound, all of that's got to create a disturbance. For a mechanical wave, the other thing I have to have is a medium. I have to have something that's going to transmit that wave. Water, air, the earth, the board. If I hit the countertop, and I'll get a wave that goes through the countertop. I have to have something that's going to transmit that disturbance. That's very different from an electromagnetic wave. Electromagnetic wave does not have to have a medium. Electromagnetic waves travel through vacuums. But the old classic, put the alarm clock into a bell jar and then create a vacuum, and you can see that the little clacker is going back and forth, but you can't hear it. It's because there's nothing to transmit that sound wave in a vacuum. So I have to have a disturbance. There has to be some physical connection. Air gives me a physical connection, but there's got to be something that carries that connection. And if I have a solid, that makes it easy. Even with water, it makes it easy. So mechanical waves have to have a disturbance, they have to have a medium, and I have to be able to transmit it. But the big thing is, whether it's an electromagnetic wave or a mechanical wave, all waves carry energy and momentum. So all waves are going to carry energy and momentum. So we're going to have that. There are 2 types of waves that we get to talk about. So if I think about that string, and I create a disturbance in this string, I'm going to create a pulse. And that pulse is going to propagate down the string, either way. It's going to propagate until it hits the wall. And then, when I have it hit the wall, it's going to rebound and come back. So my wave is going to be a pulse that goes through. I have 2 types of waves. And that's why I have to have my handy-dandy slinky, and I'll demonstrate here in just a second. But a transverse wave is like that pulse that's traveling in a spring. It'll be a disturbance where it'll go up, and it'll travel through the string, and you'll see it. I've got an up and down motion. That's where I'm going to have my mechanical wave. It's going to be a transverse wave. So transverse waves are going to go up and down. The water, if I put the pebble in the water, that's a transverse wave. I'm actually going to see it. Now, the other kind of wave is called a longitudinal wave. And that's where I'm going to get an area of compression and stretch, or what we call rarefication. So if I'm talking about sound, it's going to be compression and rarefication. And I will actually get that compressed. So I'm going to have Monica, I'm going to have you come up here, because you're going to be my other end. Because we're going to do a couple of waves. If I'm in my physics lab, right? If I'm in my physics lab, I actually have something that I can connect this with. So let's make sure, see if come on, teacher, come on. There we go. No. Switch view. Okay, confidence monitor shows me. You guys see me over in Enid on the screen? Because I'm not seeing you guys. Okay, cool. All right. So Monica's over here. She's standing. She's got the other end of my splinky. Go ahead, back up. Okay. Well, maybe come this way. We're gonna have to play with the camera here a little bit. Let's see. We're gonna zoom out. No, wrong way. It's backwards from what you think. Come on, keep going, keep going, keep going. I love it. Learning each room is always fun. So Brian was like, well, I probably did it last week. All right, so you guys see Monica? Okay, so I'm gonna send a transverse wave down my slinky. So I'm gonna do the pulse and you see it go from horizontal up and down. Now it's dampening, of course, because my slinky's got weight and all that good stuff. And so I get my dampening back and forth and I get that pulse that goes up and down. Now when I do a transverse wave, I'm gonna send an area of compression and an area of rarefication going back and forth. So when we look at that spring, the spring gets the compression and rarefication as it goes back and forth. That's a longitudinal wave. You guys will probably see on a test, draw a picture of a transverse and a longitudinal wave and tell me which one's which. So you need to know the difference between a longitudinal and a transverse wave. Both waves have amplitude. Okay, I'm going to switch view so I can actually see what I'm seeing. Okay, all right, maybe. Go that way. There, that works. I got my switch view, and that, so I have those guys up there, switch view. Ah, good. We're getting it all together here. Computer, present. Great. Okay, so now I got things where I want them. So when I do my amplitude is going to be kind of tell me about that compression. Okay, my amplitude is going to tell me how that compression is. My transverse wave, it's really easy to see where my amplitude is. It's very similar to that sine wave. But I can still write for my longitudinal wave, I can still write that same wave equation that we're dealing with. So a longitudinal wave can be expressed as that sine curve or that cosine curve, depending on where we are. The compressions respond to the crests and valleys, and the stretches belong to the cross. They're also called density or pressure waves. And there's a reason that we start looking at that longitudinal wave, because sound is a longitudinal wave. I'm going to change that pressure of the air by changing the density of the air in order to propagate that wave, and I'm going to actually get that compression but going backwards and forwards. So we're going to start looking at sound. I'm going to come back on Wednesday. We're going to do some more stuff with the pendulum, just so you guys can see some more examples. But we're actually going to start moving into sound in order to keep us on track. So I'm still going to have an amplitude. The amplitude is the maximum displacement of the string when I'm doing a transverse wave. The wavelength is still between the two successive points, so we're still going to use those same definitions. We also know that the speed of the wave is going to be the frequency times the wavelength. Remember, frequency is in hertz, so it's 1/seconds. Wavelengths are in meters, so it's going to be meters over seconds. So when I'm dealing with my sound wave, I'm going to have that same velocity equation that we already know. And so it's derived from that basic speed equation, and it can be applied to all types of waves, even electromagnetic waves. Except when I deal with electromagnetic waves, we kind of already know what the speed is. But mechanical waves, we're going to have to use the frequency and the wavelength. So we're going to stay right there with those frequency and the wavelength. So if I can also translate this back to how heavy is my string. We all know that if I have a string, let's start with a thread. If I take a piece of thread and I create a wave in my thread, how fast the wave is going to go through my thread is going to be dependent on how thick the thread is. So when I go to a cable, all right, when I go to a big heavy rope cable, I know that my wave is going to be a little different because the mass of my cable is different. We also know this if I play a stringed instrument, like a guitar. If I look at the guitar strings, certain guitar strings have a different mass to them than other guitar strings. So I will have a different types of mass that's there. And we know that the speed is going to be related to how we're going to hear sound. And we know that that's going to be also how we're going to start dealing with it. So the velocity through a string or a rope or a chain even if I take a big length chain, I'm gonna have and it's gonna have to be under some kind of tension, because if I'm trying to play a stringed instrument and I want that string to create tension, we know I'm not gonna get any sound out of it unless I have tension. I can actually calculate the velocity of the wave through that string. It's going to be the force divided by mu, where mu is my linear density of the string. It's the mass per unit length. So the velocity of my sound or my wave through a string is going to be dependent upon what tension is I have in the string and what the linear density of the string is. So the speed is going to depend on the properties of the medium. And we already know that, because we know if I hit a rail, I know that the sound is going to travel very differently through the rail than it does through air. We know we can hear the train coming if we put our ear against the rail a lot earlier than we can when we actually hear it through the air. So, and we can do the same thing with earthquakes. You can actually hear an earthquake, but the sound is going to travel at a different speed through the air than it will through the ground. So we're actually going to see different speeds. That's how sonar works, because we know the speed of sound in water. We know the speed of sound in air. Your next experiment that you guys get to measure is you're actually going to measure the speed of sound in air. One of the experiments that you get to do this semester is actually do that. So we actually will measure the speed of sound in air. And so we'll look at it. We also know that if I take two pebbles, and so I've got a placid pond, and I take two pebbles, I take one pebble and I plop the pebble in and I get those lovely concentric rings, right? The concentric rings move out. And I plop a second pebble in, those waves start to interfere with each other. And the waves can constructively interfere and they can destructively interfere. So my waves can add amplitude. If I'm in phase and all that lovely stuff, my waves will constructively interfere and they'll get twice as big. And we've all done this. You've sat in the bathtub as a little kid and you've created the bathtub as a little kid, right? You've created the bathtub and then you got in time with the wave and the wave got bigger and bigger until it ultimately sloshed out of the bathtub. Or if you've gone to like any of the big water parks, they've got a wave pool. And how do they generate that wave to make that wave get bigger and bigger and bigger? They do it so that they're in phase and that amplitude gets bigger and bigger and bigger. You do it on a swing. When you give that push at just the right point, the amplitude gets bigger and bigger. But if you give the wrong push at the wrong time, we stop. So I can have constructive and destructive interference. So waves obey what we call the superposition principle. They can be additive. We can add things up. Now, if I'm doing something with sound, if you've been ever in a concert hall, there are certain places in the concert hall where there's no sound. It's dead. Because that's a spot where I get destructive interference. That I cancel everything out. That's what noise canceling headphones are doing. They're creating waves in there so that they're canceling out the extraneous noise that you hear. So so waves do obey what we call the superposition principle. So it says when two or more waves encounter each other while moving through a medium, the resulting wave is found by adding together the displacements of the individual waves at that point. So we will be able to do it. And we find that it really only is true for small amplitudes, but we know that we can have it happen. It does happen. So let's look at the constructive and destructive interference. So the two ripples in the pond, that's the one I described to you just a second ago. We can see that we get constructive and destructive interference, and you can see it and actually diagram it. So destructive interference is when they're going to cancel out. Constructive interference are when they're going to be additive and add together. So I'm going to actually have those pieces going back and forth, and we actually utilize that. So just looking at it a little more, two waves, if they're in phase, they're going to constructively interfere, and the amplitudes will get bigger. Two waves that are completely out of phase, their amplitudes are going to cancel each other out, and they're going to be flat. And I can have combinations anywhere in between. So let's look at traveling waves. So in this case, I've got a little traveling wave going this direction, and a big traveling wave going this direction. And as they come together, you'll get strange waveforms. When they're completely in phase, that's when I'm going to get the maximum amplitude. But then they travel through each other. So two waves traveling in opposite directions, the net displacement when they overlap, they add together. But the big thing here is that the waves, when they travel through, they're unchanged. Just at those points where they're additive, where I'm at on my string, am I going to see a difference? But the waves themselves remain unchanged. So we get constructive interference and destructive interference. You get the same thing with destructive interference, you'll get that different pattern, and the pulses are unchanged after the interference. So we can get a lot of different things that are out there. So now let's talk about waves and when they encounter some other kind of disturbance or an edge. So when I have a wave that hits and I have a fixed end, when I have a fixed end, the wave is going to reflect, and now what you actually see is some of that constructive and destructive interference, and the wave will actually, a transverse wave will actually flip over when I have it, if I have a fixed end. But the shape remains the same. The wave will invert if I have a fixed end, but the shape actually remains the same. If I have an open end, I don't get that inversion. That other end is allowed to move around. And what we're going to see in a little while is that when I have a fixed end, I create what we call a node, particularly when I'm dealing in sound with organ pipes and stringed instruments and things like that. I'm going to create a node. With an open end, I'm going to create something that we call an antinode. So we won't get that inversion if I have an open end or that end is free to move. So I'll get that. That takes us to the end of this presentation. On Wednesday, what I'm going to do is I'm going to go ahead and we're going to go back and we'll look at the pendulum. Get everything going. All right, we'll go back to the pendulum. And then I think you've got some homework I know you've got the simple harmonic motion homework is due. And I think we're still doing the simple harmonic homework is, the simple harmonic motion one is due and WebAssign is due when?
Friday, or the 29th.
The 29th, which is Monday.
Yeah.
So I think we're doing really good there. And you got some pre-work that's also due. So we'll see you guys Wednesday, unless there's any other questions. All right.
I need to find it.